Walkthrough of discussion 13, problem 3, randomized algorithms basics. So this problem has a bit of a long description, so we'll go over the important parts for the first problem and we'll kind of revisit this description as the information here is relevant to us. So first we're given a general description about the philosophy or idea behind randomized algorithms. So in general, whenever we are analyzing randomized algorithms, we want to always take into account bad events, right? Essentially, when our randomization process, we see here, makes our algorithm fail. And in general, it's helpful for us to calculate the probability of these bad events in order to get a general bound of the success of our randomized algorithm. And we can also use this bound to demonstrate some other ideas that we'll show later in this problem. In this specific problem, we are given some graph G, and it has n left vertices and n right vertices with n squared minus n plus 1 edges. And then we are looking to prove that G always has, or prove that G always has a perfect matching. And then to give a polynomial time algorithm and n to find this perfect matching. Actually, I forget what. As a quick reminder, for a perfect matching here, what we are looking for is essentially a set of edges such that every vertex in our graph is touched by exactly one edge. So for example, if you had a graph that looked something like this, a perfect matching could be composed of this edge as well as this edge because we see that every vertex is touched by exactly one edge. This would also work, but something like this would not work. Because as we can see here, these two vertices are touched by more than one edge. Similarly, if we just had something like this would also not work because these two vertices are not touched by any edge. So that's the definition of a perfect matching. Now we're given a randomized algorithm called blind matching that we're going to use in order to create a randomized algorithm that has a chance of solving the perfect matching problem. And we're given essentially these two mapping functions, and they're uniform and independent random permutations of n. And then it's going to output, essentially this is a matching. And if it's a valid matching, we're going to output it, otherwise we're going to output failed. So a quick way to break this down, since there's a decent amount of ideas here, so it's easy to get lost on what this algorithm is doing, is essentially remember that we have n left vertices and n right vertices, right? So we have essentially our graph looking like this. And remember, it's a bipartite graph, so we always have edges from the left going to the right and right to the left, vice versa. The idea here then is that these two functions are essentially mapping numbers. So we can think about it as like pi of 1 could yield something like 2, right? Essentially, this could be any random number from 1 through n. And the same thing for our other function. So then what you can think about here is essentially what this is going to do is it's going to generate a bunch of random pairs of vertices such that each vertex only appears once in the left and right side, and it's going to effectively randomly select edges that may or may not be present in our bipartite graph. So as an example, if we were to choose n to be 4 here, so we have 4 left vertices and 4 right vertices, one potential matching could look like 2, 3, 1, 2, 3, 4, and 4, 3. So then that would correspond to, on this graph, a matching that might look something like this, where we go 2 to 3, 1 to 2, 3 to 4. Oh, and it looks like we used 3 twice, so we'll have to do 4 to 1 here. So that would correspond to a matching like this, where all these green edges may or may not be on the graph, right? Essentially, the idea is that this output just outputs pairs of vertices. So if the edge is there, then it's a edge that we can include in our matching, but obviously if the edge is not there, then we can't include it in our matching. So that is an instance where we can see that this algorithm would probably fail. So that's what this else statement is referring us to. There's a little bit of math here about union bound, so we'll take a look at this in a second and revisit it when it becomes relevant in our problem. But for now, we're going to move down a little bit. And so here we can already see this instance of indicating essentially our bad events, right? So again, as a brief recall, remember we're trying to look at bad events. So our bad event in this case, which we've seen from running our algorithm, is really when we select an edge like this, but this edge isn't actually present in our graph. You can see that is indicated by xi here, where some pair is not present in our graph, and we're asked what is the probability that this occurs. For this problem here, the most straightforward approach is going to be a counting-based approach, right? So we know that one of the ways we can compute a probability like xi, so probability of xi equaling 1, we can essentially treat this as like the total number of like possible outputs of our algorithm over essentially the number of like wrong or like bad outputs. All right, because the probability that we choose an edge that's not present in our graph is essentially like if we look over all the edges that we could output, how many of them are bad, and then the probability is essentially the number that are bad over the total number of edges we could output. So firstly, what is the number of potential edges we could output, right? What we're really asking for here is what is the number of possible pairings like this we can make? Well, we can look at this by counting, and we know that we have n choices here and n choices here. And because of that, we can say that the total number of outputs is n squared, because there's n choices for the first value, n choices for the second value. In order to get the number of wrong outputs, we actually have to look back to our definition of our graph G, and we're told that it has n squared minus n plus 1 edges. So remember then, using our same logic, that if this graph G was like a complete bipartite graph, it would have n squared edges, which effectively means then this graph is missing this many edges. Right, because this is the amount of edges that are in the graph, this is the amount of edges that are in a full graph. So if I subtract these two and I get n minus 1, this is the number of edges that are not present in our graph, right? And then what you can think about is that what would happen if you selected one of these non-present edges? Well, then that would be a wrong output, right? So from there, we can see that the number of wrong edges that we could possibly output is n minus 1, because any wrong edge is essentially an edge that is missing from our graph, and there are n minus 1 edges that are missing from our complete bipartite graph. So that's going to be our probability that xi is equal to 1. Part 2 then is asking us to use union bound, which we skipped over earlier, and we're going to use that to upper bound the probability that m is not a perfect matching. So looking at union bound here, what we're told is that given some not necessarily independent Bernoulli random variables, so xi to xn, then we have the following identity, where the probability that the sum of these Bernoullis being greater than 1 is less than or equal to the sum of the individual probabilities. So breaking this down, remember, what did xi mean to us? Xi was the chance that some edge we selected was not present in our graph, right? Now, what does it mean for m to not be a valid perfect matching? Remember here, what are we doing? We are getting all the possible, or we're getting essentially all the edges we want to include in our perfect matching. And then we're going to output yes or no if it fails or not. And what determines a no in this case? So remember that a no is determined as long as even one of these edges is not present, right? Because if one of these edges is not present, then we can't actually construct our valid perfect matching, which means that everything fails. So essentially you can think about M not being a perfect matching as the same thing as this probability, right? Because this is really checking if one of these Bernoullis is true. And if any one of these Bernoullis is true, it means that edge is missing. So essentially it's asking the probability that at least one of my edges are missing. That's the equal phrasing of M is not a valid perfect matching, right? So upper bounding this, because these values are the same, we could then upper bound it with this, right? So I can say the probability that M is invalid, well, given our analysis just now, we know that's equal to the probability that any x1 to xn summed is greater than or equal to 1. And this is going to be less than or equal to, by our union bound, the sum of all the probabilities of xi equal to 1 from I equal to 1 to n. We know we just computed from part 1 that this probability is going to be n minus 1 over n squared, so that's going to be sum from I equals 1 to n of n minus 1 over n squared, which is equal to n minus 1 over n. Just like that. Part 3 then is to conclude that G has a valid perfect matching. So this is actually a pretty interesting component of probability here, where in part 2, what did we calculate? We basically just calculated the probability that M is not a valid perfect matching, or essentially the probability that our algorithm fails for any, or the probability that our randomized algorithm will fail for any specific run, which then consequentially means the chance that our algorithm succeeds is going to be 1 minus that, right? So it's going to be 1 minus n minus 1 over n. This is the probability that M is valid. And again, note that as a expansion of this statement, we can say that M is valid on any graph, right? So it's the probability that M is valid on any graph, because we can take into note that all of this here, we never made any assumptions about the way our graph looked besides what was given to us, besides our guaranteed properties, essentially, which means that our probability we calculated here is true for any graph. And the idea here is that this is a non-zero value, right? It doesn't actually matter at the end of the day whether there's like a 1% chance, a 0.001% chance that this algorithm has a potential of succeeding. The idea is that because this algorithm has a non-zero probability of success, it implies that the solution must always exist, right? The principle being, if a randomized algorithm has any chance of actually finding the solution, then that solution must be present. And that's just something we are able to say because we know this probability is never 0. So from there, you can conclude G has a valid perfect matching. So because probability of success is greater than 0, then all G have a perfect match. We'll discuss a technique called amplification, where in general the idea is that if we have a randomized algorithm that fails with some probability p, you can repeat that algorithm and aggregate your results in order to now essentially have the same algorithm, but it has a much smaller failure probability. So we'll talk about an example here called spam blind matching, where spam blind matching, what it's going to do is it's going to run t times, and then if at least one of the runs is valid, it's going to output that run. Otherwise, it will say it failed. So what is the tight upper bound we have on spam blind matching? Well, we know that from above, the chance that anything fails, so the chance that a single run fails is going to be n minus 1 over n. So that's going to be n minus 1 over n. So then the chance that spam blind matching is going to fail is essentially going to be the chance that everything fails, right? So we have we have t runs, and the idea is every single one we have a fail. So fail, 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 dot, 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 fail. So what is the chance that this occurs? That's the probability we're calculating here. And that's essentially just going to be this value to the power of t. Part 2 then asks how large should we set t if we want a failure probability of delta. So if we want a failure probability of delta, this is mostly just some like mathematical massaging, but there is a observation here, which is that n minus 1 over n to the power of some, we'll say, or sorry, if you raise this to the power of n, it's going to be less than or equal to 1 over e. The way you're going to use this is essentially, then if we know if t equals n, then it's going to yield a value that's less than 1 over e. Then if you do this to, for example, n times 2, we know that this is going to be 1 over e squared. So the direction we're going to go with this is if you do n ln of 1 over delta, then what you can do here is when you apply that here, this is now going to be 1 over e. So now we're saying this is to the power of t. Then you can say this is going to be equal to 1 over e to the power of ln 1 over delta, which means that this is going to be 1 over delta, which means this is going to be equal to delta. So that's how you would select t in order to make sure you have a Philip probability of delta. The main thing is just this observation on the inequality here. So if this wasn't immediately obvious, I wouldn't worry about it. However, the math after should be relatively understandable here. Now we have some introductory problems to Markov's inequality. So for our first one here, we're given Markov's inequality where x is a non-negative valued random variable, and then for every t greater than or equal to 0, we know that this is true. We're first going to prove that Markov's inequality is false for random variables that can take on negative values by giving an example. So one example you could use here is simply a Bernoulli random variable that is going to be, a random variable here that can be 1 or negative 1 with probability 1/2 on each. Why is this? Let's take a look. If we look at the expected value here, we see that the expected value of x is going to be equal to 0. So then we're going to say the probability that x is greater than or equal to any t. So for example, let's set t equal to 0. So the chance that x is greater than or equal to 0 is going to be less than or equal to 0 because our expected value is 0. But we clearly see that this is not true because the probability that x is greater than or equal to 0 is 1/2 because we can select this one. So this is a quick, easy way to disprove Markov's inequality for negative valued random variables. Part 2 is similar in terms of constructing a counterexample. So we're going to give a tight example of Markov's inequality. In particular, for some given mu and t, construct a random variable x such that the expected value of x is mu, and the probability that x is greater than or equal to t is equal to mu over t. So we're constructing, so we make an x such that e of x is equal to mu, and then the probability that x is greater than or equal to t is equal to mu over t. So effectively, we are mostly focusing on this part where the expected value of x is equal to mu. There are many ways to do this. One way we're going to choose to do it is we're going to have our random variable be equal to t with probability mu over t, and then 0 with probability of the rest, which is 1 minus mu over t. We can see that the expected value of this is going to be t times mu over t plus 0, which is going to be equal to mu. So then that checks the expected value requirement. And in terms of the probability, we simply substitute in this value for our expected value of mu. And then that tells us that our probability here of x being greater than or equal to t is less than or equal to mu over t. And then if we look at our random variable that we have defined here, right, the probability that x is greater than or equal to t, well, the only option here is equal to t, right? So this option here, the chance that this occurs is directly mu over t. So that's a tight constraint on this. So that is a way we have constructed our random variable here in order to make this true. Part here we are asked about Chebyshev's inequality. And Chebyshev's inequality is defined below as for any x as a random variable with a well-defined variance, then this inequality here is true. We're going to be using this inequality in the following problem, so we'll mostly go over the problem and come back to Chebyshev's inequality when it's useful. But in this problem, we're given a bag with n balls, k of which are red, and the remainder of which are blue. And we don't know what k is, but we want to estimate k from L independent samples with replacement drawn from B. And then we're told to let x be the number of red balls sampled. So essentially what we're doing is we're sampling a subset of the balls, and from there we're going to try and predict our value k, given our ratio of L over our number of samples drawn. First, we're told to figure out E of x. So as a reminder, x equals the number of red balls sampled. And the probability of any x, right? So we can use linearity of expectation here since it's hard to get all of the balls. We can say E of x is equal to the value of E of x1 plus x2 plus x3 ... And essentially what we can say is that each of xi is a Bernoulli, where it's going to be 1 if red ball and 0 if not. So from here we can say, well, what's the chance we get our red ball? That's going to be n over k, right? Or sorry, k over n, which makes the opposite true with 1 minus k over n probability. So then, from here, we can simply use linearity of expectation to add up our expected values, and that's going to be k over n. And how many samples are we doing? We're doing L samples, so it's going to be k over n times L. So that's going to be E of x right here. Now, with regards to our variance, so we're calculating the variance of x. Something to note here is because we are drawing with replacement, these are going to be independent samples. So we can actually state here that our variance here is again going to be broken down into x1 ... plus xl. And then we can further say it's going to be equal to the sum of the variances of each variable. And this is because we have independent samples drawn. Lastly, the variance of a Bernoulli, so variance of xi here, is equal to p times 1 minus p, just as a principal. So then this is going to be equal to k over n times 1 minus k over n. This is true for any Bernoulli, which means here this is going to be equal to L times k over n times 1 minus k over n. And that is our variance. Part 3 here is going to be a bit more complicated. We're told to choose a value for L and give an algorithm that takes in n and x and outputs a number k tilde such that k tilde is within some range of the true k. So as a quick reminder, remember that we don't actually know what k is in this problem. We're trying to estimate k, where k is the true number of red balls that actually exist in our bag. The way we've been doing this is we've been trying to get a ratio of red balls, right? So remember here, we are drawing L independent samples. X is the number of red balls that we sample from our L samples. And this ball has a total, or this bag has a total of n actual balls. So in that sense, we can imagine that what we're doing really is we are creating a ratio of X over L. This is kind of the ratio of red balls we've sampled from the total samples we've done. And if you're trying to get an estimation of k, we'll call k tilde, this is going to be equal to x over L times the total number of balls, n, right? The idea then is that this is like our assumed or hypothesized ratio of balls that are red. And if we multiply this by the total number of balls, this should hopefully yield us a rough approximation of the total number of red balls that are in our bag. 2 follow-up questions then, since we're estimating our k tilde, right? So another key insight here is that when we see that we want to output a k tilde such that it's bounded with some probability within a range, that likely means we're using Chebyshev's because of this absolute value here, right? So this bound and these absolute values correlate, which means we'll likely use Chebyshev's inequality. And our first steps there then are to calculate an expected value and variance for our new variable k tilde. So what is the expected value of this variable? Well, we can simply substitute in our old variables. And we know what, since L and N are constants, we can bring them out, but we have the expected value of X calculated right here, which means we have N over L times K over N times L, and we can see that all these cancel out, and that leaves us with an expected value of K. Logically, this makes sense to us because our expected value of our estimation of K should ideally equal K. So that's a good sanity check to do, to note that we have correctly made our K tilde random variable. As for the variance, we can again write it the same way. So it's going to be X over L times N. And then we can again substitute it in. So we have here, this is going to be L K over N times 1 minus K over N. And the only other thing to note here is that when bringing these constants out of the variance, you actually have to bring out the squared. So it's going to be N squared over L squared times this, which means our value here is going to be equal to N K over L times 1 minus K over N. And while it's more correct to leave it in this form, for simplicity, what we're going to do is we're going to bound this by simply NK over L. So we're going to drop this second part here, where it's multiplied by K over N. And we're just going to essentially take this. And that's just for simplicity of math moving forward. Given these two values now, we can set up our Chebyshev's inequality. So in order to set up here, what we're going to do is remember that we are calculating the probability of, in this case, K prime So in this case, we're calculating the probability that we deviate from our true mean, so that's K tilde minus K. The chance that this deviates in the amount we're allowed to let it deviate by, we say. So that's going to be this greater than sign. We are given it as epsilon root K, right? So we're going to write down the actual value, which is going to be, for now, T root, and then our variance, which is NK over L, but we're going to keep in the back of our minds that this, ideally, we're going to sub in a value for L, right? Remember, our very first part of the problem, we're choosing a value for L. We're going to sub that value in such that this value is bounded by epsilon root K. Now filling out this probability, it's going to be less than or equal to, and remember that we want this to have probability at least 1 minus delta, which means this is going to be bounded by delta. Because of the fact that Chebyshev's inequality is written as the chance that we are greater than our ranges as less than or equal to this, which means that we want to be less than or equal to delta because this essentially is the bound of us this is the probability of us exceeding our bound, while this is the probability of us being in our bound. So then if we're subbing in delta here, we're going to make a small note that 1 over epsilon, or 1 over t squared here, is equal to delta. And writing this out again, that means t is going to be equal to the square root of delta. So we can sub that in right here. So that's going to be a probability that k tilde minus k is greater than root delta square root nk over L. This. And finally, we can make our final observation that we have here. We're going to essentially be picking a value such that these are equal, so that's going to be oh, and as a quick note, sorry, this is 1 over square root delta, so this is 1 over square root delta here. So then we have 1 over square root delta square root nk over L is equal to epsilon root k. And this is going to occur, we can see when we're picking for L, well, L has to equal, first off, it has to cancel our value of n out because we don't see any n terms. So we're going to have n, and then that k we can leave. And then on the outside here, what we're going to see is we should have a delta to cancel out this 1 over square root delta. And then in order to get the epsilon term here, we need to have a epsilon square term. Right, so that's just more of a pattern matching way of recognizing it, and we can verify this by writing it out. So we see this cancels, and then everything else becomes 1 over square root delta times square root of k. Actually, this becomes square root of k times this, right? And we can tell then from here that these two are going to cancel out, and that's going to become square root k, and then epsilon. And that's going to be equal. So we're going to pick our L to be this value in order to achieve our probability. And that is a walkthrough for question 3 on discussion 13. Thank you.